In this video, we're going to apply the integration by parts formula to the integral of x e to the 4x. I will also lay this out in a way that makes it more straightforward to remember the procedure. The integration by parts formula has a u and a dv in the integral we're given, so somehow we have to split all of this into a u and a dv part. For now, I'll do that for you, and then we'll investigate the subtleties of how to choose these in a most appropriate or most effective way. But for now, let's just split this right here. We're going to call the x part u, and we're going to call e to the 4x with the dx. This puts the d things on an equal footing. Again, think of them usually as a small interval of x and a small interval of this new variable v. And we see that u times dv is going to equal everything we started with. So in integration by parts, everything in the original integral has to be in our u or dv. Once you've made that choice, we turn a crank. As soon as we have those definitions, then we want to find du. How do we get a du out of this? Well, we differentiate our u, and that just gives us a 1. Or we can rewrite this, bring the dx up. We have a relationship now for du versus dx, a fairly simple one, thank goodness. The other step is to integrate. So this is a derivative step, and this is an integral step. I'll just put the integral because we already actually have the dv's and the dx's that we need. The integral of dv, well, what's that? Implicitly, if there's nothing inside the integral, then there's a 1 multiplier. And so we're saying, what would we differentiate if v is my variable and get 1? Fortunately, it's really simple, and it's always going to be the same. This side will always give us a v back. Then on the second part, we have the integral of e to the 4x. Notice that's different from the first integral. There we had a product of functions. Those are implicitly hard. It's hard to find a simple antiderivative when you'd have to use the product rule to go back and check it. But now we are only integrating the e to the 4x by itself, and that we can do by guessing and checking. The integral of e to the 4x will be e to the 4x, but it'll need an over 4 in there as well. We're going to skip the plus c. I'll explain why at the end. But we could include it if you wanted. It just turns out not to be helpful. It'll always end up merging with something else anyway. So we just integrate and find the simplest antiderivative of the dv part. So where does that leave us? We're now in a position to actually use this formula. We had our original integral, u dv, and now we're going to write it out in a new form. So x e to the x dx is equal to u times v. U times v can be captured by moving along this diagonal, and if you always write out your u and dv left to right, and then fill in the rest of these elements in the way we did here, we're going to find that this diagonal is what we're looking for to capture u times v. So let's write that out first. U part and v. And then we're going to subtract the integral of v du. And that is just these two elements together here. V is e to the 4x over 4, and du is the same as dx in this example. V du. And that's the process. We've turned one integral into another integral with some stuff that no longer needs integration or handling or anything. This is essentially done. We just have to focus our attention on here and ask, is this simpler? And I would argue this is absolutely simpler than what we started with, x e to the 4x, because this does not have a product of functions anymore. This 1/4 we can bring out front, and this is usually a typical step here to tidy it up. So we'll have x over 4 e to the 4x minus 1/4 the integral of e to the 4x dx. This is definitely doable. In fact, we have already done it before. We know what that integral is. So we can do our integration now on the part that we have left. We get minus a quarter out front, and then this exponential, when we integrate it, gives us another dividing by 4, and here's where the plus c creeps in. When we evaluate our final integral, we get a plus c at the end. So what we've learned from this example is the integral of u times dv can be applied to a function that we're given, especially if it's a product naturally, and a substitution doesn't seem to fit. Once we've taken our given integrand here, including the dx, we broke it into our u and dv, we turned a crank and we got to a new form of the integral, some other functions minus another integral, and this new integral was simple enough that we could integrate it and eventually end up with a formula for the antiderivative of x e to the 4x. All of that being said, this formula does not look simple. Especially in early examples, it's worth checking that what we're doing here actually makes sense. We're going to do that on the next page. I'm just going to copy here. So we found this function here was our antiderivative. How do we check? Well, we differentiate it. Then we find the derivative of this, and our goal is that this should equal x e to the 4x. That's what we started with in our integration, so we should be able to get back to that through the derivative of this statement here, or this function here. Let's just make sure that's true. First term's the hardest here because we have a product rule, so we're going to have 1/4 e to the 4x plus the first times the derivative of the second, that's e to the 4x times 4. So all of this comes from the derivative of that first term. Then we have minus 1/4, I'll leave this quarter here for a second, because we're going to differentiate e to the 4x, which is going to give us another 4, like so. And then the plus c disappears with the derivative. Now this still does not look an awful lot like x e to the 4x until we start canceling things. I'll do this over a few lines just so we see exactly what's happening here. The 4's here also cancel, and there we see our x e to the 4x. And the other two terms are perfectly balanced. We have negative 1/4, positive 1/4, those cancel, and sure enough, our final derivative value is x e to the 4x. This is not an obvious antiderivative. Going back to the last page, this is our overall antiderivative of x e to the 4x. You would not have guessed this. All the constants, the two terms, one of them being a product of x and e to the 4x, the other one just being an exponential by itself. Not at all obvious, but the integration by parts process generated it for us, and we can verify that it is correct. When we do the integral, we get to this formula, and we know that this formula is correct as an antiderivative because when we take it and differentiate it, we get back to the x e to the 4x. Perfect.